Hey Wheat North, Mr. Yergler here. This video is going to talk about titrations. I'm not going to go into the calculations with titrations that much because it's really just stoichiometry, but I want to focus on the titration curves and kind of identifying different types of titration curves. So let's get started by looking at what a titration really is and how it's kind of set up. You're always going to have a burette full, and that's usually full of base, almost always full of base. Occasionally we'll put the acid in here, but that's a little more rare. And in the, this is called the analyte, in the flask, you're going to have your acid. Now, as you add the base to the acid, you're slowly going to neutralize it. The whole purpose of this is to figure out what is the concentration of the unknown solution in the beaker or in the flask down here. Now, you can kind of track this with a pH meter or a pH probe, but a lot of times we'll also use indicators, a colored solution that changes color at different pHs. And we're trying to reach the equivalence point, what's called the equivalence point. Make sure you have a definition down for that. It's really simple. It's just when the moles of acid that you started with are equal to the moles of base that you've added. And that's regardless of whether the acid is strong or whether the base is strong. Now, there's also what's called a endpoint. And the endpoint is where the color actually starts to change. So that's applicable to when you're using a color indicator. Now, if you look at this, at the way this curve is shaped, the endpoint is actually very far from the equivalence point in terms of pH, but because it's so close to the equivalence point in terms of volume, it is actually a pretty good way to do the titration. So even if your indicator is changing color at about a pH of 10, that's going to be so close to the volume of where the equivalence point was that it's close enough for our purposes, essentially. Now, there's a couple different types of titration curves. We're going to start by looking at a strong acid with a strong base. This is probably the most straightforward one there is. And then we can also look at a weak acid with a strong base. Now, at first glance, these look very similar to each other, but in fact, there's some really notable differences that I want to point out. First of all, notice where we're starting on our curve. So these are always pH on the y-axis and the amount of usually the base added on the x-axis. With a strong acid, because it's strong and it's 100% dissociated, we're starting at a very, very low pH. Whereas with the weak acid, this is assuming we're starting with the weak acid in the flask or in the beaker, and we're measuring the pH of that at our initial conditions before we add any base. Notice that the pH is relatively high compared to the strong acid, and that's because the weak acid is only partially dissociating. A lot of times just 1% or less, and so the pH isn't going to be quite as low when you're starting out. Now, the other thing to note is where the equivalence point is. With a strong acid, strong base, it's going to be exactly at 7. Because both are fully dissociating, you're going to end up with a neutral salt. With the weak acid, strong base, the equivalence point is actually a little bit above 7. And that's because the base is strong and the acid is weak. Let's look at that in a little more detail. So notice what's down here at the bottom. We have the weak acid is acetic acid or ethanoic acid, and the base is NaOH. Think about what reaction that would produce. When we're at our equivalence point, we're going to have a solution essentially of sodium acetate. I'm writing it like this because I want to show that the ions are in solution. It's not really an actual salt. And then water, which is going to be neutral. Now, at that equivalence point, when we have equal moles of our two reactants, is the sodium going to go back to sodium hydroxide? No, not at all, because it's a strong base. Could the acetate ion hydrolyze, grab an H off of the water to go back to its undissociated acid form? Yeah, that's definitely going to happen because it's a weak acid. It's going to reach an equilibrium with the undissociated acid, leaving behind an OH, which then leaves our final pH a little bit high. We've neutralized all our acid, but because of the hydrolyzation of the acetate ion, we're left behind with a little bit of OH minus. Now let's look at a strong acid with a weak base. I'm going to show you two different curves. They're actually of the same thing. This one looks just like all the other ones because we're starting with an acid and we're titrating with a base, so it ends up basic. In this one, we've flipped it. So now we have the acid in the burette and picture the base in the beaker, and that's what we're tracking the pH changes of. So we start with a basic solution, and then as we titrate the acid, it ends up acidic. But it's the same thing. It's still a strong acid with a weak base. And you can see the difference in the x-axis there. In this one, it's labeled as an alkali, meaning a base is being added. In the other one, it's not quite as clear, but where I got the picture from, it was labeled as adding the acid to base. Let's take a look at a couple main features of these curves. We're starting, I'm going to refer to the one on the left. We're starting at a really low pH, so that's consistent with a strong acid. And in the other one, we're ending with a really low pH, so that's consistent with a strong acid as well. Look at where the equivalence point is. It's below 7, right? That's the key idea here, is that the equivalence point is below 7 because we have a weak base. So just like how the weak acid in the other curve was hydrolyzing to leave behind some OH-, this weak base is going to hydrolyze to leave behind some H+, and so it leaves it slightly acidic. And then notice where we end up. The curve kind of flattens out at a pH above 7 because we've now added enough base to overcome the acid, but it's not so high that it's up close to 14. Because it's a weak base, it kind of flattens out relatively close to 7. It's kind of noteworthy in this one that the titration curve dips right away at the beginning. And that's because we're starting with a weak base, but we're adding a strong acid to it. So that addition of that strong acid causes an immediate dip in the pH, and then it kind of enters this buffering range where we have the midpoint, and then it reaches the equivalence point. Speaking of the midpoint by definition is when the moles of acid is equal to half the moles of base. So you're halfway to the equivalence point. The noteworthy thing about this is at the midpoint, the pH is equal to the pKa. And we haven't really talked about pKa's too much. It's just the negative log of the Ka. But this is super helpful for identifying when the equivalence point is going to be because we can know where the midpoint is. The same is true of this titration. At this midpoint, your pOH is going to be equal to the pKb. So it just depends on where you're starting, if you're starting with an acidic solution or if you're starting with a basic solution. So that's really all we need to go over with titration curves. You should be able to identify the titration curve of any combination of strong acid, weak acid, strong base, weak base, and kind of highlight those main features and kind of draw conclusions off of the titration curves that you're given. All right, this is Mr. Euler signing out.